The correct answer is E, 0.318 nanometers. The speed of any wave is the wavelength times the frequency, and this is equal to c for an electromagnetic wave in vacuum. Solve for the wavelength and substitute the values of the speed of light in vacuum and the frequency of the X-rays. Recall that the unit of hertz is equivalent to inverse seconds, or 1/seconds. The seconds cancel, leaving meters. So the wavelength is 3.18 times 10 to the minus 10 meters, or 0.318 nanometers. On the electromagnetic spectrum, X-rays have short wavelengths and high frequencies. Only gamma rays are higher frequency and shorter wavelength than X-rays. On the other end of the spectrum, radio waves have long wavelengths and small frequencies. Radio waves can have wavelengths as long as hundreds of kilometers. The visible part of the electromagnetic spectrum is around 10 to the 14 hertz. The visible wavelengths range from about 700 nanometers to about 400 nanometers. EM waves that have wavelengths just a bit shorter than 400 nanometers are called ultraviolet, or UV, and EM waves with wavelengths just a bit longer than 700 nanometers are called infrared, or IR. Between IR and radio waves are microwaves, which have wavelengths on the order of a meter. When an electromagnetic wave travels in vacuum, its speed is c, the speed of light. But when an electromagnetic wave travels in a material that's not a vacuum, then the speed of light decreases due to interactions with the atoms in the material. That interaction is characterized with a value called the index of refraction, n. By definition, n equals c over v, the speed of the wave in vacuum over the speed of the wave in a material. So the speed of an electromagnetic wave in a medium is c over n. This table lists a few examples of different mediums and their corresponding index of refraction. N is 1 for a vacuum, and just a little greater than 1 for air. But then the index of refraction increases substantially more for denser materials. Orange light has a frequency of 5.09 times 10 to the 14 hertz and a wavelength of 589 nanometers when traveling in a vacuum. When it travels from vacuum in a diamond, its speed decreases. What's the speed of the orange light when it's in the diamond? You can use the speed of light in vacuum and the index of refraction for diamond, 2.42. When traveling in the diamond, the light has a speed of 1.24 times 10 to the 8 meters per second. When this light travels from vacuum into diamond, its frequency remains the same, but its wavelength changes. What's its wavelength when it's in diamond?